Hi everyone, welcome you all to Deep Matrix. It's been months after I'm doing this video, so without any further ado, let's move to the topic. Today's topic is in control systems, we see about what is non-minimum phase transfer function. So I have an article for you, which would be better for your understanding. So we'll start with what is transfer function. So we all know transfer function is the mathematical model of a model, which is the ratio of Laplace transform to the output to the Laplace transform of the input. The main advantage of using the transfer function is if we want to know how the system performs at at an instant t, then this could be very helpful. So this transfer function can be defined only for the linear time invariant systems. So what is non-minimum phase transfer function? So we all know from the transfer function we can define zeros and poles. So I'll show you a demo. Let's declare a system of TF, say 1 2, which is nothing but s plus 2 1 3 and 2. So yeah, this is the transfer function that I have used there in the MATLAB software. This can be typically represented using these numbers. If you don't know how it works, see my video on transfer functions. So I am defining that. So a system has been defined, so I am printing it. So this is my system. So now we'll plot the pole zero map of the system so that you can view the poles and zeros diagrammatically. Okay, it's running, it's taking time, sorry for that. Okay, here we got our pole and zero. So as you can see, since it is positive, the pole is located at -2. You can view it using, see there is a 0 here, so that is at point 2. And when we find factorial to this, so we'll be getting values as -1 and -2. So in a nutshell, we can say that all the poles and zeros were present on the left half of the S-plane. So the response will be stable and causal. So we'll plot a step response to it. System, I think, see, this is the step response. So it is very clear, it's keep on increasing, and at some point it is reaching the value 1. So this is the step response of the system. As you can see, there is no delay in it. So as soon as the input has been given, the output starts to retrace the input. So this is a normal system. We can also name it as minimum phase transfer function. So then what is non-minimum phase transfer function? um, so non-minimum phase transfer function is simple. Instead of here I am having a pole at -2, if I have a pole at +2, which means the zero should be sorry, I mentioned it wrongly. Here I am having a 0 at -2. Instead of at -2, if I have a 0 at +2, then we can call it as non-minimum phase transfer function. It is very simple. The poles will be present on the left half of the S-plane, whereas the 0 will present on the right half of the S-plane. So this is the typical example of non-minimum phase transfer function. So what is the disadvantage of it? We'll see that. So I'm defining the system 2. So the same code, but the thing is, instead of 1 I will give -1. The pole value will be same, 1 3 and 2. Okay, I'm creating a new figure 4. See, we'll see the PZ map first. See, in this case, one pole is present at -1 and another pole is present at -2. So but in the last case, here we have another 0, but in this case the 0 has been moved to +2. So this is the example difference between minimum phase and non-minimum phase. The thing is, but moving the pole from left half to right half has the effect on step response. We'll see that now. Figure like some random 7. Now step of SYS2. See, wait. Okay. See, in case 1, that is in minimum phase transfer function, when I give the input, the output starts to retrace the input. But in this case, there is a small delay. I mean, there is a small dip in the step response. So after the dip, it starts to recover and to retrace the input. So the only difference between non-minimum phase transfer function and minimum phase transfer function is this delay. This delay is due to the 0 present on the right half of the S-plane. So I'll tell you how it works. See, this is a transfer function that we are having, but we can split this transfer function like this. S plus 2 multiplied by 1 divided by S square plus 3S plus 2. So if you multiply this, you will get this system. So see here, the 0 is in direct contact with the input. So we, from this diagram, we can say that zeros of the transfer function has the ability to modify the input, whereas the poles of the system determine the stability and response of the system. So by this we can define that. So here, after splitting this, we'll take this S plus 2, that is the 0. We'll take an inverse Laplace transform. So here I am giving step signal, so U of S has been multiplied. So when I take the inverse Laplace transform, so this S will be multiplied with U of S. So inverse Laplace transform of S, U of S is, we all know this S will be converted to differentiation. So d divided by dt into ut plus 2 U of S is nothing but 2 ut. So here you see, so this is the step input that I am giving. So this dut will be added to the 2ut, so that the output will be amplified in this case. So this is for minimum phase transfer function. But if the value of S becomes minus S, then there will be no difference, but the minus will be added here. So minus d divided by dt into ut plus 2 ut. So in this case, instead of this dt, there will be small minus d by dt will be here. After that, 2 ut will occur. So this minus d dt by ut is the reason for the delay in the transfer function. So this is the output response. So the non-minimum transfer function will have a delay, whereas the minimum phase will not have a delay. The most typical example is, in all of our homes will be having water heaters, like solar water heaters. But in early in the morning, when we open the tap, at first few minutes we don't get a hot water. It will be very cold. So that is the delay time that it took. After the delay has been overcome, the hot water will be poured out. So this is the typical example that I could ever think of to explain you this concept. I hope you enjoyed this video. Meet you in the next one. Until then, enjoy learning. Thank you.